Hey everyone, welcome to this video on optimization. Optimization is where we find the minimums and maximums using calculus for worded problems. All the mathematics in this chapter we have done before. It is just practicing in worded problems. So let's have a look at this first graph. I have the blue line. I've made the y-axis dollars, and this is the amount of dollars a shop earns in an hour. And then I've got the hours down the bottom. So what we can see is that when x equals m hours, that they made their peak sales, their most sales, their maximum amount of sales, and that at x equals p there was a lull, and that they didn't make many sales then. So if we wanted to know those maximum and minimums, very simply, if we were given the equation, we could just graph it and press G-solve, max and min. But these questions are going to request that you use calculus to find those answers. But obviously in the test, you can check using your calculator. So let's have a look at how you would do this with calculus. Now, I know this is a bit repetitive, but some of the things I'm about to say are so important. So to find the maximum and minimums, you can find the first derivative of your equation and make it equal 0. Those answers that you get in this situation are m and p, and they are what label your sign diagram. Also, this label at the end here shows that this is the sign diagram of your first derivative. And that label is a really good reminder that everything you're doing on here to do with the points and the positives and negative come from your first derivative. Okay, so just ignore anything about the original equation. To find out where it's positive, negative, and positive, there are two options. You can either graph the derivative, and of course you would be graphing the derivative because this is a sign diagram about the derivative. And if you're graphing, you are simply looking where it is below the x-axis, because they are where the y values are negative, or above, which is where the y values are positive. Or, basically the same thing, substitute some numbers into your derivative to see if they're positive or negative answers. A reminder that if you substituted in, say, -2, you don't add that to your sign diagram, because these points that you're putting on here are the points where the slope equaled 0, and they are only m and p. Okay, I've cleared that. Now let's use this sign diagram. So we're still looking at f-x. And now we've finished our sign diagram. That is when we can start relating it to f of x. Okay, so what we know is that our first derivative shows slope. Okay, so what we have here is going to be a maximum, because we can see that we've gone up and then we've gone down. Okay, and that point M lines up with the turning point. Also, if we go down and then up, which is over here, yeah, that point P is lining up with our minimum. For some reason, they're really squiggly lines. I'm going to try and fix them. Okay, they're a bit better. Right, now, second derivative. Exactly the same process. So once you've found the second derivative, make it equal 0, and that is the thing you graph or substitute into to make your sign diagram. Now, our second derivative can actually still be used to show where there are maximums and minimums. Usually, in our previous topic, we talked about it as being concave, convex, or to do with velocity, acceleration, etc. But what we know about concave and convex is that a concave shape, which is where this is negative, is in actual fact a maximum. And that our convex shape, which is a smiley face, is actually a minimum. And so in the first derivative, our turning points, the points that we are given, m and p, line up with the turning points exactly. Whereas in the second derivative, this point here is lining up with where we change from maximum to a minimum. Okay, so oops, better not draw it like that. But basically, this whole section here is where there is a maximum, and this whole section here is where there is a minimum. So if we look up here, that point here, let's call it, I don't know, D. That's D here. Okay, so we can see that it was a maximum and then a minimum. So both the first and second derivative can be used to find a maximum or minimum. Okay, now, I was a bit lying about this graph before, because something else that we're going to consider in this chapter is endpoints. So if we go back up to our diagram here, I had actually hidden them for now, but if we actually have a look at where this graph starts and ends, which is A and B, knowing those now, if we think about when they had the greatest sales, M is actually not as high as the point B. So it's actually when it's at B hours is the maximum. If you have a look at A, that's actually not as small a sales as at P, so our minimum was correct. All that means is in the situations after you've got shown with your first and second derivatives, whatnot, whatever work you've done, you would also graph the original equation and just have a quick check over to see if any endpoints would change your answers for maximums and minimums. Okay. The questions we're going to be working with are quite wordy, and so we've got some steps to work with. So step 1, draw a large clear diagram of the situation. So a lot of our questions are going to be to do with shapes. Okay, so what's, the maximum size rectangle that can fit in this circle? So we're going to draw a nice clear diagram. We need to construct a formula with the variable to be optimized as the subject. So if you want to optimize the volume of something, and when they say the subject, they mean that would be V equals. The other thing that you want to do is try and only work with one variable. So if you've got the height of the rectangle is X, okay, so it should be written in terms of one convenient variable such as X, and it says that, the rectangle is double the length. You don't want to have X and Y. What you want to have is X and 2X. So wherever possible, you want to write everything in terms of X. Because otherwise you get X's and Y's, it makes it all a lot harder. Okay, step 3. Oh, wait, I missed something. You should write down the domain restrictions there on X. Okay, what this means is obviously for most of these situations, X can't be a negative if it's like a length. And there also might be a restriction that they tell you, for example, the maximum it could be is 20 centimeters long. Or maybe you look at the picture and you know that to fit in that shape, the maximum is 20. Because when you start to do your derivatives and things, you might get multiple answers and then you can look at them and go, well, I know which one it is because of the domains. Step 3, find the first derivative and find the values of X which make the first derivative equal 0. And so that is what we were doing earlier. Step 4, put those stationary points onto a sign diagram. You can also use a second derivative sign diagram as a test, or you can graph it to work out whether those points that you got in step 3 are maximums or minimums. Identify the optimal solution. So this is where you think maximum depending on the situation. For example, if you're looking to reduce your costs on something, it might be the minimum that you want. And remember to consider the endpoints because you might not have found those yet, but you might just need to have a look at the graph. Step 6, write your answer in a sentence to make sure you actually answer the question at hand. Okay, so let's do one. This is example 14. I've decided I'm going to actually write it out rather than just go through their writing. So, infinitely many rectangles can be inscribed in a semicircle of a diameter 20 centimeters. Okay, so a semicircle is half circle, and the diameter goes all the way across the circle. At this point here, I also wanted to show you on sector on this page. That is not it. Sorry. Loading. I have put some basic measurement formulas on this sector page where you'll find this video to have on your cheat sheet. You really don't need to know anything extreme. Circles, general rules for perimeter, Pythagoras, areas of rectangles, triangles, and circles. Surface area of a 3D shape is just when you add up all the areas. And the volume of a shape, we're going to only be working with prisms. So prisms are where it has the same shape all the way through a shape. So if you think of a chocolate cake roll, the one with the cream in the middle, it's like a swirl cake. And you cut it anywhere you cut it through the cake, it's a swirl shape. It only has to happen one way. So a prism, if you can cut it one way and it's the same shape all the way through, then it's a prism. And therefore the volume of that is really easy. You just work out the area of the end of that shape that's cut all the way through, and then you just times it by the length of the shape, and that's the volume. If that's all gone a bit fast for you, just have a read over that page afterwards. Okay, so I'll leave that there. So in our question, we want to find the shape of the largest rectangle which can be inscribed. So basically what they're saying is we could have this rectangle, we could have a rectangle like this. Which one gets the biggest, the largest area, basically, because the largest shape of something would be the area of it. Okay, so the first thing that we're going to do in this question, let's call this length here x, and then from there we're going to try and talk about everything else in the rectangle in reference to that. So if I draw the rectangle over here, I know that this length is 2x because it's I've just called one side of it x, so it's 2x width. Now, there's multiple different ways to do these questions, and so it's really just practice that helps you to recognize these things, because the things I'm going to do, you're going to go, how did you know to do that? But you sort of get used to it over time. So I would like to know the height of the rectangle in reference to x. And so one thing I know in this circle is that from here to here is 10 centimeters, half of the 20, and that goes all the way around the circle. These are all going to be 10, which means this one that goes from here to here, which is actually to the corner of my rectangle, is 10, and that's pretty handy. So for now, I am going to call this length here, the height of it, y, but I don't want to leave it as y. As I talked about earlier, you want to get everything in terms of x. So what we know for Pythagoras, so let's call this one, so this is A and B, the shorter sides, and this is C. And if I want to find B, it is B equals the square root of the long side squared, C, take away the other side squared, which is x. So B is equal to, or well, that's y really now, is equal to 100 take x squared. And so instead of calling this side y, I'm going to call it square root 100 take x squared. So now let's go from there. We want to find the largest rectangle, which is the area of a rectangle. So the area of a rectangle is length times width. So in this situation, it's going to be 2x times root 100 take x squared. If I want to find the maximum area, I could graph that equation and just press G-solve max, and it would tell me what the maximum area is. But because we're going to use calculus, it doesn't even say it in the question, but we're going to, because your test question does. And so we need to find the derivative of this. So we're going to need the product rule, because I have two parts, 2x and root 100 take x squared, and they both have an x in them. So u is 2x, the derivative is 2. V is, now actually I'm going to write that as 100 take x squared to the half. And I'm going to need the chain rule, so the power comes out the front. I rewrite what's in the bracket. That goes down to -half times by what's inside there, which is going to be -2x. And simplify those ones. So I'm going to end up with just half times -2x is just -1x or -x. And because this one is a -half as the power, the half makes it a root and the negative makes it on the bottom of a fraction. So this is going to be -x on 100 take x squared. Not that. This one. And it's nice being able to rub things out. I'm going to rewrite that one as this so that when I complete my product rule, that it's easier to look at. Okay, so then we have a dash, our derivative, is 2 times 100 take x squared. So this one times this one, plus 2x times -x on that. So that is a minus in there. Okay, so just simplifying that second part, we're going to end up with 2x times negative x. And now remember, if you have a fraction, just think of it as over 1. So it's going to be 2x times a negative x, which is negative 2x squared, and 1 times root 100, which is just root 100 take x squared. Now, instead of having a plus and then a negative, I can just make that a minus in between those. At this point here, I need to join these fractions together to simplify things. And to do that, they need to have a common denominator. So this is the denominator I'm going to be aiming for. And so I am going to multiply this number by root 100. And you know what I'm just going to do is I'm just going to move this guy over here. Give me some more space. Okay, so it's timesing by 100 take x squared over. So we're basically multiplying by 1, and again, it's like this is over 1. And so then we end up with, and I'm going to just pause. Okay, so up the top, the two square root symbols cancelled each other out. And we were left with that times that, this on the bottom. And then I just rewrote this whole lot as the second part. Now we have a common denominator, so we can bring those top numerators together. All over. The denominator stays the same when you're adding or subtracting a fraction. Let's do some expanding. Oh yes, it's going to be 2,100. Now hopefully I've got all my positives and negatives right so far, because that would mean that I end up with 200 minus 4x squared, negative 2 take 2. Okay, so I've got it fairly simplified. So now I'm going to say that our stationary points, or our maximums, our minimums, are found when that derivative equals 0. Now, because it's a fraction, only the top part needs to equal 0. Because remember, if you've got 0 out of 6, that's 0. So all we need is for 200 take 4x squared to equal 0. We could have factorized first, but you know, it doesn't matter. 50, so x is going to equal root 50. And in this situation, it's not going to be positive or negative root 50, because x is talking about the length of a rectangle, so we'll leave it as just root 50 as our answer. So let's go back up and see what this is in the context of the problem. Wow, okay, we're back up here. So we were looking for the maximum rectangle, and what we found out is that this was when x equals root 50. However, we haven't really proven whether that's a maximum. What if that's when the rectangle is at its smallest? So what we need to do is a sign diagram. And now let's think about the domain of x, like our range that x could be. Having a look at this picture, could x be any greater than 10? No, that would make the rectangle outside of the circle, because in my situation I've done x as being half the rectangle width. And so we also know that it can't be a negative number, and so we end up with a situation where we've got 0 and we've got, what did I say? Can't be bigger than 10. And in between here is root 50. And so we could graph the original equation, which would be pretty safe to do, and have a look to check that it's a maximum. Or we could graph the first derivative and see that it is above and then below, which makes it positive and then negative. So we're confident now that when x is root 50, that maximizes the area of the rectangle. And this is the step 6, which is basically write a sentence and make sure you've answered the question, because it did say find the shape of the largest rectangle. So we know we got to go back to our situation here where we substitute what we found out as x. And so this is now going to be 2 times root 50, because x is a root 50. And this one is going to be root 50 squared, and that squared and that root will cancel each other out, so it'll be 100 take 50, which makes it root 50 as its height. And that is the maximum, the largest rectangle that you could fit inside that semicircle. All finished. All right, so quite overwhelming a little bit, so have a go at these questions. I think a couple of them might start off a little bit simpler, and just keep making sure that you follow those steps, and remember that the work solution's there to give you a hint if you get stuck. All right, thanks for listening. See ya.